Okay, lesson 8.3, common logarithms at standards MA 912, NSO 1.6, 1.7, and AR 5.2. So common logarithms, which we associate with base 10, can be used for many applications. Common logarithms are usually written without the subscript of 10. We do not use the value of 10 when we write logarithms as we did before. So we would normally just write log of 2 or log of x. That is the same thing as saying log sub 10 of 2, log sub 10 of x. Most scientific calculators have a log key. On Desmos, you would use the functions feature. So if you're going to use Desmos, you're going to click on functions and then scroll to the calculus section. And then you'll find your log and log sub a, so when you're doing other pieces. Common logarithms are numbers that differ by an integral power, which are base 10. Okay, so when we look to complete the table, it says log x is equal to y, means 10 to the y equals x. So when we look at this problem, it says log of 1 is equal to 0 because 10 to the 0 power is 1. Remember that rule. Anything raised to the 0 power is 1. So log 10 equal to 1 is because 10 to the first power is 10. Log of 100 is equal to 2 because 10 squared is also 100. Log 10 to the m equals m because 10 to the m equals 10 to the m. When we look at example 1, it says find common logarithms by using technology. So it says use a calculator to evaluate log 8 to the nearest 10,000. So we're going to go into Desmos, and I'm going to show you how we're going to do that. Okay, so we're in Desmos, and down here in the bottom we see our little keypad. So when we go into here, we don't notice that we don't have a log piece here. So what we're going to do is we're going to click on functions, and then scroll down until we see the calculus section. So under calculus, we see exponentials, ln, log sub a. So we want to hit the log key. And then we're just typing in the number 8 inside. So it comes out to be 0.90308. Normally go to the nearest 10,000. So when we look at this piece to the 10,000s, we're looking at the 0 after the 3. But since the 8 is there, that's why it's going to round up to 0.9031. So remember when I said in the Desmos that we're going to the nearest 10,000 and we did the 0.90308. Those are going to the 10,000s position, so that 8 makes that 0 become a 1 and we end up with 0.9031. When we look at example 2, example 2 says solving logarithmic equations by using an exponential form. It's a science problem. It says the amount of energy E in ergs that is released by an earthquake is related to its Richter scale magnitude m by the log equation. So they gave us an equation that says log E is equal to 11.8 plus 1.5 m. Although the scale was created in the 1930s, earthquakes that had occurred before its invention have been estimated using the Richter scale. So for example, an earthquake in Cyprus in the year 1222 is estimated to have measured 7 on the Richter scale. How much energy was released is what they want us to find. So we start out with our original equation. And notice that the m is what we're replacing. For this purpose, m is actually the 7 because that's what it was measured at. So we're replacing m with 7. So now we see log e equaling 11.8 plus 1.5 times 7. So 1.5 times 7 is the equivalent of 10.5. So now we see 11.8 plus our 10.5, giving us 22.3. So now we're saying that log e is equal to 22.3. Now, but remember, we're going to go into exponential form. That's log sub 10 of e. which means I'm raising both sides to the power of 10. So you're actually writing it as 10 to the log of e equals 10 to the 22.3. So I'm saying 10 to the 22.3 power. When you use the calculator to plug this in, 2 times, you end up with a value of it's like 19 trillion, or more than that actually. It's a value of like 19 with a significant amount of commas afterwards. So we round it, saying it's basically an approximation of 2 times 10 to the 22nd power. Because remember, we're at 10 to the 22.3 power. And normally we don't deal in decimal places for our exponents. So we had to do our math, and it gives an approximation of 2 times 10 to the 22nd ergs. In example 3, it says solve an exponential equation by using logarithms. So they want us to solve 11 to the x power equaling 101. So we started with the original equation. And because we're solving it with logs, you're going to take the log of both sides. I'm taking the log of both sides. So you put the log of both sides on each side. So because now we have to do the power rule, because the x has to come down. So that x, remember, it's going to come and slide in front. So now we're saying x times the log of 11 equals 101. We're going to divide each side by log of 11. So now I'm seeing log of 101 over the log of 11. And then you plug this in the calculator. So use Desmos. And it's going to come out to be 1.9247 for its approximation. Another way of doing this is also known as change of base. So the change of base formula allows you to write equivalent logarithmic expressions that have different bases. So normally, remember, we are usually dealing with common. So common logs are base 10. So when it's not a common log, so it's like saying the log sub 8 of 17, you're going to convert it into the log of 17 over the log of 8, because we're going to follow this sequence of formulas, which says we're taking log of an, and we're going to write it doing the log of n over the log of the a value, which is our little b value. Original base. So when we look at this problem, we're going to look at example 4. It says change of base formula. So they want us to evaluate log 2 of 11 by writing it in terms of common logs. So we're going to take our log 2 of 11 and write it as log 10 of 11 with log 10 of 2. Or you can just write it as log of 11 over the log of 2 when you plug in Desmos. Because remember, we're doing common logs. So when you do that, your calculator is going to spit out that it's going to be approximation of 3.4594. Remember, you're always going to round to the nearest 10,000. Always round to the 10,000ths place, unless otherwise stated. It will always be the 10,000ths place. In example 5, they want us to apply change of base formula dealing with music. As is, a musical cent is a unit of relative pitch. So musical cent is a unit of relative pitch. It says 1 octave consists of 1,200 cents. So 1 octave is 12,000 or 1,200 cents. The formula to determine the difference. So now we have a specific formula. We want to follow the difference in cents between two notes with beginning frequency A and ending frequency B. And they have a formula they want us to use. It says n is equal to 1,200 times log sub 2 of A over B. It says find the frequency of the pitch A if pitch B, they tell us what B value is 1661.22, and the difference is 1600 cents. So they gave us the B value as 1661.22. They gave us the N value, because that's the difference value, that is 1600. We need to find the A is what we're looking for. So they gave us our formula, N equals 1200, because that's what is always going to be our sequencing for one octave, log sub 2 of A over B. So N was 1600 in this instance for us. We're going to divide both sides by 1200, and we get 4/3. And then we're going to apply the change of base formula, because we have the 4/3 on the left, not on the right. Remember, on the right, we need to apply the change of base. So that's why we wrote log 2 of A over the 1661.22 as the log of A over 1661.22 over the log of 2. We had to apply change of base here. Okay, since we are applying change of base now, in order to find our solution for this problem, we're going to use systems of equations. So we're taking our setup that we just did, and using Desmos, we're going to do y equals the 4/3, which is the left side of our equal sign, and then y equals log of, now instead of an A, we're going to use an x over 1661.22, all divided by log of 2. We're going to plug those in Desmos and then find our point of intersection. What that means is, this is what we're going to be doing. Okay, so we said we're going to use systems of equations. So the first equation is going to type in is y equals 4/3. And then our second one's going to be y equals, now because we're doing a fraction bar, we need to also do the log piece. So I want to say log, I'm going to find my log piece. So we go down to calculus, hit the log. I'm going to type in, now instead of an A, we're going to type in x divided by the 1622.2. Actually, 1661.22. Close our parentheses. And then I'm going to hit the divide key because I want to bring on the bottom piece. And I'm going to type in, I'm going to do log again. So I can go down to calculus. You could also type the word log since we're doing change base 10. And then type in our value of 2 inside. So we have our two equations, and we want to find our point of intersections, what we're trying to find. So I scroll into my, zoom out on my calculator, and I notice that I'm trying to find where it's going to finally hit its point of intersection. So what we want to do is we can do a wrench key, because I want to see how far out. On my x's, I'm going to say 0, and I'm going to go, say, about 6,000. And I'm going to do a step of 1,000 so I can zoom in easier. On my y values, we can go from a negative 10 to, say, the y value, the first one says y equals 4/3. So I'm going to say a value of 2 because 4/3 is only 1.33. So I wanted to hit the max value at 2. And I can see that our point of intersection comes in here. So when we look here, our point of intersection is at 4,186 when it's 4/3. We know our y value. We need to find our x value. So it's 4,186.01.